All right, guys, more on the Mass 6620 regression. Guys, let me step back a little bit. I think I forgot when I was talking about correlation and covariance. Um, for example, if we have an R value of 0.86, uh, another measurement we would want to look at is R squared, which is literally 0.86 squared. So, guys, let me grab my calculator. Which is 0.7396 or 73.96%. So R squared is called the coefficient of determination. And it explains the percentage of variance in our y variable that's explained by the regression on x. So for this problem, well, I just made up the 0.86, so we would say approximately that 74.0%, because percentages are usually rounded to the nearest tenth of a percent of the variance. And y is explained by the regression on x. All right, kind of regret that I forgot to cover that back in a couple videos ago, but on the good hand, it provides a perfect segue into what we're going to do here. So guys, next on the agenda is regression, and over the next few videos we're going to look at what's called SLR, simple linear regression, where we have a quantitative dependent variable that is predicted by a quantitative independent variable. And then multiple regression, we have a dependent quantitative variable, but the predictors can be quantitative or categorical for multiple regression models. Regardless, I think I just want to present this right now in terms of simple linear regression. What we have is a predicted value for a particular value of x can be found by taking the model, where b0 and b1 is the slope, b0 is the intercept, times the x value. So given an x value, we can predict its outcome by inserting the value into the model. But guys, we typically have observed data. And we'll just say we have n observations, or n ordered pairs. So we can say that y sub I, which is, for example, a value of y that we select from our data set, is equal to b0 plus b1 x sub I plus an error term for that particular observation. So guys, what we end up with is we end up with some data over x and y. We use regression techniques to find the line of best fit. So for a particular x value, we have the observed value, and then we have the predicted value. Well, the difference between the observed and the predicted is just the e sub I that I showed in the previous model. Now, guys, one thing we see sometimes, we see this model given with betas instead of b's. And guys, just remember that our b0 is a predictor of beta 0, and our b1 is a predictor of beta 1. So much like x bar is used to predict mu, these are our sample statistic, and this is our parameter for the entire population. So typically we run test of inference to see if our sample slope yields statistical significance for our population slope. All right, gang. Now let's think of what we got going on here. How do we find this line? Because you can think of this. There's infinitely many lines that could be put in to explain the relationship between x and y in this case. I mean, obviously we could do all sorts of wacky stuff, but it turns out there's one distinct line that gets the distinction, gets the honor of being called our least squares regression model. And sometimes people will call this the line of best fit. Now guys, this wouldn't be the line of worst fit, but it would be a line of bad fit. This obviously is not a very good line either, and we could get really extreme and give even worse examples of lines that do a very poor job of describing the relationship between x and y. But guys, there's one distinct line that wins out. And what I want to do now is I want to kind of show you how we actually end up finding that line. Now, there's a reason that we call this a least squares regression model, because it's the method of least squares that is used to find the values for B0 and B1. And let's illustrate that. Let's just take a small data set. One, one, two, one, three, three. So guys, if we look at that, keep it simple because it's easy to so we have a 0.11, 21, and 33. So guys, we're trying to find that one unique line. So let's think about that distance as being D1, this distance as being D2, and this distance as being D3. So we'll let our capital D be D1 plus D2 plus D3, so to speak. So we want to find the line that minimizes our D. Okay? So what we'll start out looking at is we'll actually call these our errors, because that's precisely what they are. If we examine that segment right there, what we have is the observed value minus the predicted value, or we have the observed value minus the formula for finding the predicted value. Now, we're going to move this into what's called the sum of squares. Because what will happen if we add up these values, some positive, some negative, then we're going to get a sum of D1 plus D2 plus D3 of 0. So we want to square these so our sum is a non-zero and a positive value. So what we'll do here is we'll take y sub I quantity squared, and guys, what we have created is called the sum of squares. New goal is to minimize our sum of squares. So guys, in our case, what we could do is we could let this sum be equal to q. We can sum from I equal 1 to 3 because we have 3 data points in this illustration. Typically, in general, this would be from 1 to n because we'd have n ordered pairs. So we want to find Q, which is a sum. And again, we want to find the minimum value for Q. So when we find the minimum value for Q, we find beta 0 and beta 1 that provides the coefficients for our least squares model. In other words, we find what's called the line of best fit. We obviously don't want the line of worst fit, we want the line of best fit. So let's just approach this from a very intuitive perspective, I guess. Not a theoretical one, but an intuitive one. And let's just make a guess. And when I look at this data set, 1, 1, 2, 1, and 3, 3, I think that, I don't know. It looks like to me if I just take a horizontal line at y equal 2 plus 0x, that looks like it might kind of be reasonable. So let's see what Q is. Q would be the sum of the errors squared. So guys, I missed this one by -1. I missed this one by -1. And I missed this one by a +1. So my Q value is equal to 3. Now, I wonder if I can make another guess and come up with something better. Well, I see that I could take maybe y equal x minus 1. That kind of seems reasonable. So guys, what do I get for my my y values and my predicted values? Well, my y values are the values that I get from my data set. Those are 1, 1, and 3. My predicted values are by putting the x's in. Let's just go ahead and complete the table. 1, 2, 3. So when I put 1 in, I get 1 minus 1 is 0. Put 2 in, I get 1. And put 3 in, I get 2. So my differences are 1, 0, and 1. So guys, my Q in this case is 1 squared plus 0 squared plus 1 squared, which is equal to 2. So guys, I have improved upon my Q by using this method of y equal x minus 1. But guys, as you can imagine, generalizing this would be a nightmare because there are infinitely many choices. And, we need something that provides a more theoretical approach. So guys, what we would do here, let's now generalize. And instead of taking a specific line with a specific slope and a specific intercept, let's just take the general situation. So Q is going to be equal to the sum of my y value for the first data point minus the predicted value for the first data point. The y value minus the predicted value. Plus the y value for the third point minus its predicted value squared. So guys, if I expand this out, it looks like I get 1 minus b0 minus b1, quantity squared. 1 minus b0 minus 2b1, quantity squared, plus 3 minus b0 minus 3b1, quantity squared. Now, guys, think back to Calculus 1. And if you wanted to find the maximum or the minimum value of a function, so let's say I have a function that looks something like this. And I want to find that point, which would be the absolute min. What would I do? Well, I'd find the function, I would find the first derivative, and I would set the first derivative equal to 0, and find the x value that creates the smallest. Now, I've got other places where I have x values that will be equal to 0, but I use this to find the values that have derivative equal to 0, and I can tap into the lowest value. So, since we have two variables here, b0 and b1, what we're going to need to do is we're going to need to do partial derivatives. So guys, first of all, I need to take the partial of q with respect to b0, right? So when I do that, I'm going to use the chain rule, so I'm going to have 2 times, okay, I'm looking back at what I wrote here, so I'm going to have 2 times 1 minus b0 minus b1 times the derivative of the inside with respect to b0 is just negative 1. Second term, I have 2 times 1 minus b0 minus 2b1 times the derivative of the inside is negative 2. And I have 2 times 3 minus b0 minus 3b1 times negative 3, right? No. b1, 3, yeah. Okay, so guys, my partial would be negative 2 plus 2b0 plus 2b1 minus yes, that's not right. This should be a minus 1. Doing with respect to b0, Douglas. Yeah. And this should be minus 1. Guys, my bad. I was going ahead and doing b1. I was a step ahead of myself. You guys were probably screaming at the video. So so here we're going to have negative 2 plus 2b0 plus 4b0. And then we get negative 6 plus 2b0 plus 6b0, b1. Because obviously it should be b1s. I should have used m's and b's. So much easier to keep straight. Alright, so I have a negative 2, so I have negative 10. And the b0s are, see, 4. So plus 6b0. And 2, 6, 12, plus 12b1. So let's keep that on the back burner. Now I want to take the partial of q with respect to b1, which I've sort of already done because I got messed up back here. So I guess with respect to b1, All right, let's see if we can expand this without making an arithmetic error. So we get negative 2 plus 2b0 plus 2b1 minus 4 plus 4b0 plus 8b1. So we have minus 18 plus 6b0 plus 18b1. All right, so we have 2, 6 minus 24, 2, 6 plus 12b0. And so we have 2, 10, 28 plus 28 b1. So now what we want to do is we want to solve these two simultaneously. So what I'm going to do there is, so I have 6b0 plus 12b1 equals positive 10. 12b0 plus 28b1 equals positive 24. Guys, I'm going to use my calculator there. Just use matrices. I think that's, to me, the easiest way to do this. So I'm going to set up a 2 by 3. So 6, 12, 10, 12, 28, 24. And then use matrix techniques. Call RREF, row ref, reduce row echelon form. It's my 1170 students call it row ref. All right, so what we get is we get that in the upper left position is clearly my B0s and lower is for my B1s. So I get that B0 is what, negative 1/3. And B1 is equal to 1. So guys, what this tells me is that my model is negative 1/3 plus x. Now, before we go any further to get into really cool stuff, let's we could go ahead and see what our Q is, but let's just jump over to R real quick, and we got a super small data set here, so shoot. I messed up. Guess my X should be. So if I want to look at my linear model of Y predicted from X, you can see that my intercept is negative 1/3 and my slope is equal to 1. So, I thought it was important that you guys see the just a glimpse of the theory behind creating the method of for the method of least squares. Guys, what we can do here also is we could find our Q. So our Q is going to be the observed value. And guys, again, let's look at our data set. So these things here are our observed y's. So my observed y for the first point minus all right, plus my observed y And for the final data set, my observed y is 3 minus the predicted value. All right, let's see if we can figure this out. So this would be what, 2/3, so 1 minus 2/3 would be 1/3 squared. Here we have negative 4/3, negative 4/3 would be negative 2/3 squared. And last we have 3 minus 2 3/3 will be positive 2 1/3 squared. So guys, looks like to me that's what, just 2/3, right? Yeah, positive 2/3. I didn't trust myself. So guys, that would be the minimum value of the sum of squares for any line that we could use to fit these ordered pairs. So guys, that's all I got for this one. It's going to get fun. So look forward to teaching you more. Take care.